Excellent. Well, it's my pleasure to introduce Art Fortini with Sierra Madre Mountain Rescue Team. His team has an amazing reputation, and Art has an amazing reputation. And when I came into the Mountain Rescue Association in 2004, one of the first presentations that I was intrigued with was Art's presentation back then, where he had just won an award to do research in this area. And I know he's done a lot with it since. So without any further ado, Art, thank you for coming on tonight.
Okay, thank you, Michael. All right, let me go ahead and get the screen share going. Okay, can everyone see that?
You're looking good.
Yep, and we just lost it. Let's try that again.
Just a quick comment while Art's getting the AV together is if you have questions, please hold them or actually put them in the chat box. And at the end of the presentation, I'll read them off to Art. So no questions, make sure you're muted and we'll move forward.
Okay, so let's go forward with this. Thank you for the introduction. And I'd like to thank everybody for coming out to watch my presentation this evening. The fact that you view this as more interesting than the Olympics is humbling. So tonight we'll be talking about snow anchors and some of the things that you could do right, and we'll also talk about some of the things that I've seen people do wrong. So hopefully by looking at a few of those things, we'll learn from other people's mistakes and not fall into those same problems ourselves. So a little outline, we'll talk about the effects of the snowpack and how that impacts the integrity of the anchors that you're building. We'll talk about different ways to build a snow anchor, and there's no shortage of those. There are many ways that you could take multiple tools and combine them together into a snow anchor. And as it turns out, based on the testing that we did, most of them are not terribly useful. Then we'll talk about the dynamic behavior of snow anchors. What happens if you have an oopsie in the field and you put a shock load on your system? And then finally wrap things up with some real world considerations. So the goal of the exercise tonight is to help you understand the strengths and weaknesses of different types of snow anchors. And what we want you to do is be able to make an educated decision as to which type of anchor to use when you're confronted with a given situation. And one of the points I would really like to make is that one size does not fit all. If you only want to learn one type of snow anchor, that's not a good way to do things. If you're only going to have one bullet in your gun, it's best not to show up to a gunfight. So what we want to do is give you the confidence to deal with a situation like this. What would you do if you knew this was coming? Okay, so looking at the big picture, you have a series of links in your chain of your system that include both software and hardware, and ultimately in the case of snow anchors, the snow is what's going to be supporting the load. Now, in the testing that we've done over the years, we have broken pretty much every link in that chain at one point or another. We've broken the snow lots of times, and ideally when you're building a snow anchor, this is what you expect to fail. But we've also broken pickets, flukes, and carabiners, which are things that you don't necessarily expect to fail. And we've also broken some soft goods, including a main line. So if you can build a snow anchor that's strong enough to cause you to fail a main line, that means you got some pretty good snow that you're working with. All right, so let's talk about the effects of the snowpack, because ultimately that's what's going to be supporting the load. So the mechanical properties of the snow are really what's driving the train. And there are two different properties of the snow that really come to the forefront. One is the compressive strength of the snow, and one is the shear strength of the snow. And I'll talk a little bit more about what that means in a few moments. You also want to know whether the snow is dry and powdery or if it's moist and cohesive. If you have cohesive snow, that's actually going to work in your favor and make the snowpack amenable to modification and strengthening. If you disturb the snow and then give it time to settle, that could potentially, not always, but potentially make the snowpack stronger and make your anchor stronger. You also want to know about whether or not you have layering in the snowpack. If you have weak layers in the snowpack, that's obviously not a good thing. If you have icy layers in the snowpack, however, that could potentially work in your favor since ice tends to be pretty strong. You could drill down to another level and start looking at the microstructure of the snowpack. What do the actual snowflakes and grains in the snow look like? You can look at the pore size distribution in the snow. What's the bulk density of the snow? What's the moisture content, the temperature gradients, yada, yada, yada. All of those things that the avalanche people like to look at with a little hand lens, you could look at those when you're assessing your snowpack for snow anchor qualities as well. But you don't need to go to that level, okay? As a rule of thumb, keeping it simple is the better way to do things. And you want to just answer two questions. Are there layers in the snowpack, and does it pass the snowball test? Okay, you want to keep it simple. This sort of stuff is not keeping it simple. Okay, you don't need to do integral calculus. You don't need to dig a snow pit that's 2 meters deep. The type of information you need to know, you can get that simply by walking on the snow, and when you dig your little trench to bury your snow anchor, take a look at what's going on inside that little trench that you just dug. Okay, know your snowpack. Do you have icy layers or weak layers? As you're digging your trench to bury the picket, the fluke, the whatever, pay attention to what's happening as you're digging that hole. Okay, push your hand down in that trench and feel around. If you feel an area of granulated sugar, that tells you have a weak layer. If you find a nice icy layer, well, that's a high strength zone, so you want to take advantage of that. Other things you can do is just pay attention to the snow as you're walking on it. If you're sinking in up to your knees, that tells you one thing. And if you're barely scuffing the surface of the snow, that tells you something completely different. You could also probe the snowpack with your ski pole or your ice axe. The snowball test, this is a test that we developed a long, long time ago, and it's just as useful today as it was back then. If you can make a snowball and being a nearby team member with it by throwing it as hard as you possibly can, that tells you that compacting the snow is going to strengthen it. Okay, that also tells you that the snow is a little bit on the warm side and it has a certain amount of moisture associated with it because surface tension in the liquid water is part of what's holding it together. If you pass the snowball test, that means that compressing the snow and compacting it is going to make the snowpack stronger. So if you have the luxury of time, then what you would want to do is compress the snow where you're going to be building your snow anchor to increase its density and increase its strength. However, the flip side of that is also true. If you try to make a snowball and it just falls apart in your hands, that tells you that disturbing the snow in any way is going to weaken it. So what that means is that you want to keep the snow that you're going to build a snow anchor from, you want to keep that absolutely inviolate. Don't let people walk on it. Don't let people disturb it. Don't let people throw their equipment on top of it. Anything you do is going to weaken an already weak snowpack. So you want to be very, very careful to avoid damaging the little bit of strength you have in the material to begin with. Now, one of the questions that everybody always asks is, well, how strong is the snow? And the answer is it varies tremendously. It's going to vary with the slope aspect, the time of day, the elevation, all those things that the avalanche people are concerned about, the snow anchor people should be concerned about as well. Strength numbers are pretty meaningless unless you're dealing with snow that is identical to the snow that you did the testing in. And by identical, I mean very, very, very identical. Talk more about it later, but if you were to build a dozen snow anchors in the same snowpack on the same slope with the same aspect at the same elevation and test them, you're not going to get the same number. You actually can get quite a range of numbers. And that's one of the things that makes dealing with snow anchors, I'm not going to say more of an art than a science, but something where you want to be very, very careful. That's the sciencey side of it. Then there's the gut feel. When you're digging the hole to bury the tool, how strong does that snow feel? Is it Sierra cement or Cascade concrete, something that's high density, high strength? Or does it feel completely insubstantial, like champagne powder in Utah? Guy here with the bad hair day, he summed it up really well. I don't know if you can read that. It says, the intuitive mind is a sacred gift and the rational mind is a faithful servant. We have created a society that honors the servant and has forgotten the gift. I'm an engineer by training, but I definitely appreciate what he's trying to say there. Okay, with a snow anchor, you're building a life safety system, something you're going to trust somebody's life to out of snow. The material is extraordinarily weak. Steel typically has a strength of about 100,000 pounds per square inch. Snow on a good day, maybe 1 pound per square inch. So it's 100,000 times weaker. I mean, you could crush it in your hand, right? That tells you how weak this stuff is. As I mentioned, the material properties vary tremendously, and they're typically unknown when you're building the anchor. Snowpacks don't have a little hang tag on it to tell you the 3 sigma breaking strength. And that's a consideration. Pretty much everything else in your system will have that hang tag that tells you how strong it is, but the snow doesn't. So here I'm going to present to you some data that we've collected over the years to underscore the fact that snow is super, super variable in terms of its mechanical properties. Okay, here are different snow anchor configurations, the min and the max strength of the data that we collected, the average and the standard deviation, and the 3 sigma mean breaking strength. The 3 sigma MBS is what you get if you take the average, so in this case, say 514 pounds, and then subtract off 3 standard deviations. So gear manufacturers do this so that 99.9% of the equipment that they sell you will have a strength that's greater than the 3 sigma MBS that's stamped onto the side of that piece of equipment. And if you look at the snow anchors, what you see is that pretty much all of these, the mean breaking strength is less than 0. So if somebody tried selling you a carabiner with a mean breaking strength of, say, 0, you probably wouldn't want to trust your life to that. But that's what the data on snow anchors tells us. The only thing that had an MBS greater than 0 was a human being in self-rest position. But all the rest of these, there's just tremendous amounts of scatter. So that's your first red flag to be very, very careful when building a snow anchor and use lots and lots of redundancy. Never trust your life or anybody else's to a single point of failure or a single snow anchor that's buried in the snowpack. Okay, what keeps us safe though is our ability to keep the applied loads very, very small. Okay, you don't hear much about people doing crevasse rescues and then having rescuers falling into the crevasse after the subject that they're trying to pull out. Okay, and the reason we get away with that is we keep the load small. We restrict it to single person loads wherever physically possible. If you have to send an attendant over the side to manage the litter, it's best to put that attendant on a separate set of anchors on a separate rope, just to keep the forces independent of each other. Another thing you could do, particularly in a crevasse rescue scenario, is to put something at the lip to reduce edge friction. My first time doing crevasse rescue training, I thought, that's snow, it's ice, it's slippery. We don't need to put an ice axe or an edge roller near the side there to reduce friction. And then I tried pulling somebody up out of the crevasse and learned that I was woefully wrong. Putting an ice axe or something smooth at the lip makes a huge difference in terms of reducing the amount of friction. And then finally, the last bullet point there, avoid dynamic loads. A, it's bad form, and B, it increases the loads on the system, and C, it actually will decrease the strength of your anchor, and we'll talk more about that in a little bit. Okay, I mentioned there are 2 types of failure modes. There's compressive failure and shear failure. In compressive failure, the hardware is just going to simply pull through the snowpack. This is analogous to a loose powder avalanche, or more correctly, a piece of hardware being pulled through a loose champagne powder snowpack. This type of failure mode is typically associated with low anchor strengths, but the failure is usually graceful. You can see the anchor moving through the snowpack. You know what's happening. You know what to expect. However, if you have compressive failure and you find a weak layer, then when your snow anchor enters that weak layer, your picket, your fluke, whatever, the failure could be sudden and catastrophic. So if you're dealing with a snowpack where you anticipate compressive failure, you want to use hardware that has a lot of frontal area. The flip side of that is shear failure. This is where you get a cohesive wedge of snow that pops out of the snowpack as a unit. So think of it as a small hard slab avalanche, where that volume of snow that you're popping out of the snowpack is the slab. This type of behavior typically gives you a very high strength anchor, but it is not graceful failure. Typically, it fails all of a sudden and without a whole lot of warning. One of the nice things about this is that the strength is determined by the area of the shear wedge, that chunk of snow that you're pulling out of the snowpack. And you can actually estimate what that size is going to be. And if you're looking at a snowpack where you believe that you're going to be dealing with shear failure, as a rule of thumb, bury the hardware as deep as possible, because that will increase the size and the surface area of the shear wedge that gets popped out of the snowpack, which in turn will increase the strength of the overall anchor system. Okay, so anchor types. Okay, for the most part, we'll be dealing with pickets and flukes, but we'll also talk a little bit about dead men and bollards. Okay, your traditional picket, and this is what you see in pretty much every mountaineering book ever published, is you place a picket nearly vertical, you tip it back a few degrees, into the snowpack, you clip to the top of the picket, and you're good to go. Very quick to place, but it is also the weakest possible configuration for a snow anchor. Talk about the more common failure modes we've seen with these, and I'll do this for each type of snow anchor so that you know what to anticipate if you start to see these things happening. For a traditional picket, vertical placement, top clip, the most common failure is going to be compressive failure in the front of the picket near the surface of the snow. So the stresses on the snowpack are going to be greatest right in this area here. And what will happen is that the picket is going to rotate forward. And what happens once that picket rotates past dead vertical, there's now going to be an upward force acting on that picket. So now the picket is going to want to slide up and out of the snowpack. So once you see the picket start tipping from the backwards configuration towards a vertical configuration, all sorts of alarm bells should be going off in your head. You want to do something to reduce the load on that picket before it ends up in this configuration and exits the snowpack. This type of failure mode happens a lot more quickly if you start off at the top of the picket some distance above the top of the snowpack, because that's just increasing the bending moment that you're placing on the system and the compressive load that you're placing on the snow. And there's no rule that says that the carabiner up here has to be at the surface of the snow. This whole thing could be buried a foot down. So if you have an icy layer a foot down, you want your carabiner to be just above the surface of that icy layer so you can take advantage of it. As a rule of thumb, though, a traditional picket is not a high-strength anchor and not recommended for rescue systems. Now, this is a vertical place picket in a snowpack where the picket literally had to be pounded into position. So here we're talking just a few steps away from glacier ice.
6.3.
Okay, we're getting past the vertical and it slides up and out of the snowpack. That particular picket, because we're dealing with super high density material, tested out to just a little over 1,000 pounds. But this is highly unusual. In anything but super high density, high hardness snow, your strength is going to be much, much lower than that. So recommendations, traditional picket, you want to do the snowball test. If it passes the snowball test and you feel compelled to use a trad picket, compact the snow in front of the picket. That will give you at least a fighting chance of being able to hold body weight. If it fails the snowball test, don't use a traditional picket. As a rule of thumb, longer pickets will generally give you higher strengths. You want to set the top of the picket just above an icy layer if there happens to be an icy layer. If there's a weak layer in the snow, then you want the top of your picket to be below that weak layer so you're not using that weak layer to support any of the load. As a rule of thumb, though, traditional pickets are generally too weak for life safety applications, unless you're dealing with snow like that video I just showed you. Okay, horizontal picket placement. Some people refer to this as a dead man placement. I don't, because the word dead man is used in a variety of different contexts out there to mean just about anything that you bury in the snow. I've seen it applied to flukes. I've seen it applied to improvised anchors. So for this type of picket placement, we're going to refer to this as the horizontal picket. So it's a mid-clip placement. And to build one, you simply dig 2 perpendicular trenches. Generally speaking, deeper is going to give you a stronger anchor. You're going to clip the center hole of the picket, place it horizontally in the trench, and then backfill both trenches with snow from behind the anchor. You don't want to backfill the trench with snow from in front of the anchor, because what that'll do is decrease the effective depth of burial. So you're removing material from an area that could otherwise be supporting the load. So always backfill your trenches with material from either behind the anchor or from way, way off to the side of the anchor. Common failure modes. Compressive failure is what you'll get in moderate density snow. The picket will form an ice wedge and travel through the snowpack as you continue to apply load to it. This tends to be a rather graceful failure mode. You'll see your carabiner or whatever, your virtual anchor, moving through the snowpack at a steady rate as you apply steady force to the system. Now, a moving virtual anchor generally will make people feel very, very uncomfortable, myself included. If it moves a few inches, I'm not going to lose any sleep over it because pretty much all snow anchors, when loaded, are going to move a few inches. If the thing is moving a few feet, that's going to make me sweat a whole lot more, regardless of how cold it is outside, because I don't know what the anchor is going to encounter next. And that lack of certainty is very unsettling. Okay, the other common failure mode that you'll see with the horizontal picket is shear failure, where we eject a monolithic block of snow from the snowpack. So we have our picket back here, very nice and horizontal. And then this wedge of snow pops out of the snowpack because we exceeded the strength of the snow surrounding that wedge. This tends to happen very suddenly and very abruptly. Fortunately, though, it typically happens at very, very high loads. So if you prompt this to happen, it means that you did something cataclysmically wrong in terms of overloading your snow. Another common failure mode that we see, particularly in high density, high strength snow, is failure of the picket itself, where we tear the carabiner through the eye of the picket. This typically happens much, much more likely with 3-foot pickets than with 2-foot pickets. And the problem with the 3-foot picket is that you get a much bigger bending moment way out at the tip of the picket that causes what we refer to in the material science world as a biaxial stress state. By bending this thing like a boomerang, you're putting this area of the picket into tension, but the carabiner is loading it this way in compression. And because you have multiple forces acting on the piece of metal that used to be right here, it gets very unhappy with you and it fails. For a 3-foot long picket, frequently you see this happen at about 1,000 pounds, whereas for a 2-foot picket, typically it's closer to 2,000 pounds. Now, realistically, if you're putting 2,000 pounds onto a single placement in a snow anchor, you're doing something very, very, very wrong. Okay, if you're out doing testing, yeah, load it up until you see failure. But in an actual rescue scenario, there's absolutely no reason where you should be putting 2,000 pounds onto a snow anchor. Okay, so recommendations. If you fail a snowball test, leave the snow in front of the anchor undisturbed and use the longest picket you have, something with the most surface area that you could get away with. If you pass the snowball test, then if you have the time, go ahead and compact the snow in front of the picket, increase its density and increase its strength, but throttle back on the size of the picket and go with the 2-foot pickets. So you can avoid that bending moment and this type of failure mode that you see in the background. One thing you want to be careful of with the horizontal picket is the presence of weak layers in the snowpack. If you have a weak layer or an icy layer, place the picket below that layer. Okay, the Sierra picket. This is one that Gordy Smith and I kind of invented up on the slopes of Mount Rainier during one of the test series we did many, many years ago. It's a vertical placement with a mid-clip. To place one of these, you dig a trench for the leash that extends from the picket in the direction of pull. And you want that depth to be at least half the length of the picket. So if you're dealing with a 2-foot picket, you want that trench to be at least a foot deep. Deeper is better. And you want to make the width of that picket as wide as the heel of your boot. So you'll probably be digging that trench with the adze of your ice axe, which is not going to be wide enough. So you're going to want to exaggerate the width of that trench so that you can compress the snow at the bottom of the trench with the heel of your boot. So you're going to compress the snow in front of the anchor, dig your trench, then compress the snow at the bottom of the trench, clip your tether to the center of the picket, place the picket vertically at the back of the trench, tipped slightly backwards, slightly meaning about 15 degrees, give or take. Then backfill the trench with snow from behind the placement and thoroughly compress that snow that you're backfilling as you're backfilling it. So put some snow into the trench, stomp it down, put some more snow in, stomp it down some more, put some more snow in, stomp it down some more. Okay, if this is done correctly, the only failure mode that you're likely to see is going to be sudden uplifting of the snowpack. So this would be very similar to what we described with the horizontal picket, except it'll be a larger volume of snow with a greater surface area on the sides. So typically, the Sierra picket configuration is going to give you a higher strength than a horizontal picket configuration for a given carabiner burial depth. Typically, this is going to be a very strong anchor. Another failure mode that we've seen is if you don't backfill the trench adequately. So if the snow that you use to backfill the trench isn't quite as strong as the snow that you stomp down at the bottom of the trench, your picket is going to rotate forward because this snow here will be providing greater resistance to travel than this snow here. Once the picket starts to rotate and goes past 90 degrees, the same thing that you saw happening with a traditional picket can happen here as well. And this picket will now try to slide up and out of the snowpack. One point that I would like to absolutely emphasize is that if you fail the snowball test, you cannot use a Sierra picket, because what it's telling you is that the snow that you're placing here will have zero strength. Okay, as you're backfilling the trench, it is imperative that the snow that you use to backfill it be strong. And because you had to dig out and excise the snow from the snowpack and then put it back later, if you fail the snowball test, the snow will not be able to support a load, and this anchor will literally fail to the point where you can pull it out with your hands. So if you fail the snowball test, do not use a Sierra picket. Okay, so recommendations. First bullet there, don't use it if you fail the snowball test. You want to compact the snow in front of the picket at the bottom of the trench and do it again as you're backfilling the trench just so you maximize the compressive strength and the shear strength of the snow. Because this is typically a high strength anchor with a lot of force on the hardware that you bury, 2-foot pickets are recommended over 3-foot pickets. And you want to be aware of icy layers or weak layers in the snowpack. If you have an icy layer in the snowpack, then ideally you want to put your carabiner right up against that icy layer to maximize the amount of strength that you get out of the system. Flukes. Flukes are one of those things that have fallen in and out of vogue. If you look at very old editions of Mountaineering, Freedom of the Hills, flukes were the go-to hardware for snow anchors. Then a couple of editions later, it was all pickets. And in the most recent edition that I looked at, they don't even mention flukes. To place a fluke, you want to dig 2 perpendicular trenches. Deeper is generally stronger, so the deeper you go with the fluke, the better off you are. Clip the wire rope to your tether that's going to go to your virtual anchor. Place the fluke in the trench with both cables nice and taut. Okay. If the rake angle of the fluke is adjustable, then you want to set the fluke perpendicular to the snow surface. So the rake angle is this angle here that I refer to as beta. Now, most flukes, this angle is going to be set at the factory by the little ferrule that they swage onto the cable right about here. However, some manufacturers, I own one by DMM, they allow you to rotate the fluke relative to the cables. And in the testing that we did, we invariably got greater strengths with the fluke located or oriented perpendicular to the direction of pull. Now, the standard dogma is if you have this at some angle that's determined by the factory, that as you pull on the fluke, it's going to dig itself deeper into the snowpack and hypothetically make the anchor stronger. Now, I personally disagree with the logic there. When I go rock climbing, if I place a cam or a stopper into a crack in the rock, I place it where I want it to stay. I don't want it to move around in the hopes that it somehow finds a stronger or more favorable location to wedge itself in. Okay? If I place it right here, I want it to stay right here. And the same is true with snow anchors. I don't want my fluke wandering through the snowpack trying to find a new home. So going back to placement, dig the 2 trenches. The trench that's perpendicular to the direction of pull doesn't need to be that wide, just has to be as wide as the fluke itself. Then go ahead and backfill the trenches with snow from behind the snowpack. And go ahead and, if you pass the snowball test, compress that snow as best as you can. Okay, common failure modes, same as the horizontal picket. You can either get compressive failure as shown on the left, or you could get shear failure as shown on the right. If you're getting a compressive failure and you're using the factory settings for the rake angle, then you want to be careful because your fluke can dig itself deeper into the snowpack and find a weak layer or an icy layer, either of which can have catastrophic results. Whereas if you have shear failure, now that's sudden abrupt slab avalanche type of failure, It tends to be a very strong anchor, but one that doesn't let you know that it's about to fail. Okay, bollards. These take quite a bit of time to set up. What you want to do is dig a teardrop-shaped moat pointing in the direction of pull. And you'll want to pad the back and uphill side, and particularly the corners of the bollard. These things can be surprisingly strong, even in extraordinarily dry powder. So here's an artist's conception of what these things look like. On the uphill side, you want to put some padding there. You could use a pack, a jacket, a fluke or a picket, a rolled up foam pad, or actually an unrolled foam pad to cover as much of this acreage as possible. Anything you could do to spread out the force from the webbing or rope that's over here over a larger area of snow will work in your benefit. Common failure modes that we've seen are shear failure of the mushroom stem, if you will. So if you apply enough load to it and you have a weak layer that traverses the snowpack, you can cause that entire top layer to shift. The other failure mode that we've seen is the rope or the webbing cutting through the snowpack. If you fail to padding up here or something to distribute the load, this is something that's going to happen. In some of the testing that we did, though, this is not as big of a problem as you might expect. You certainly don't want to prompt it to happen. So if you have something available, by all means, put some padding here. But I'll show you some drop testing that we did with an unpadded piece of soft good around the anchor. Okay, so recommendations, larger is going to be stronger and more robust. If you pass the snowball test, then you want to compress the area from which the bollard is going to be dug. If you fail the snowball test, then you want to go ahead and leave that snow undisturbed, and you want to make the bollard as large as possible. And you also want to pad the uphill aspect of the bollard. During one of the lectures I gave on this, one of the people in the audience suggested the concept of a 30-minute bollard. If it takes one person 30 minutes to dig a bollard, that's about the right size. And that's independent of snow conditions. If you're chipping a bollard out of glacier ice, your 30-minute bollard is going to be fairly small. Whereas if you're shoveling champagne powder out of a snowpack that you sink in up to your armpits to make the bollard, that 30-minute bollard is going to be substantially larger. And in the testing we've done, yeah, the 30-minute rule of thumb seems to hold water. The downside of a 30-minute bollard is if I fall into a crevasse and it's going to take you 30 minutes to build an anchor, you're probably not doing me any favors. Okay, dead man. This is an improvised anchor, so you want to be extremely cautious with this. So what you're going to do is tie a tether around the centroid of some large, strong object. And you want to make sure that the object is strong enough to not bend or break or tear under the expected loads. So if you have a ski or a pair of skis or a snowboard, that's something that you could rely on to have good strength. You want to be careful with the metal edges on these pieces of equipment. So if you're dealing with skis, you can put the two skis face to face, or put the skis with the metal edge facing downward, and then use a basket hitch rather than a girth hitch, so that the material that's connected to the ski board or the ski or the snowboard is not bending over that sharp edge. Things you don't want to use would be a stuff sack filled with snow, because ultimately the strength of that anchor is going to be determined by the strength of the ripstop nylon comprising the stuff sack. And that's probably not going to be strong enough that you want to put somebody's life on the line with that. Going back to placement, you want to dig a hole for the object and a trench for the tether, and then backfill the trench and the hole with material from behind the placement. Okay, so this is an artist's conception of a ski with a downhill binding on it. You can tell I'm not a very good artist. But the black layer here, this would be the metal edge that surrounds the ski in this particular example. So if you girth hitch this, or just simply tie a loop of rope around it, so I have a bowline or a figure eight over here, have it so that the soft good is tangential to the sharp edge. If you girth hitch it, then one side or the other is going to make pretty much a 90-degree bend over that edge, and that will seriously decrease the strength of your anchor. Okay, so failure modes that we have seen, we have girth hitch skis and we have cut the webbing, failed at about 1,000 pounds. The snow didn't fail in that case, it was the nylon that failed. So basket hitch would be your friend in this situation. The other failure modes there with the question mark, those we have not actually seen. And I'll chalk that up mainly to the fact that we haven't done a lot of dead man anchor testing. But if you take an item that's oddly shaped, there's the possibility that oddly shaped item will rotate, and then your basket hitch or girth hitch could slide off the end of the item. If you bury a stuffed sack full of snow, you could potentially tear through the nylon comprising the stuffed sack. If you pull hard enough on it, then you could get shear failure like you would with a horizontal picket or a fluke or a Sierra picket, and simply extricate a solid wedge of snow from the snowpack. So recommendations, whatever it is that you're burying, usually the larger it is, the stronger your anchor will be. And usually the deeper you bury it, the stronger the anchor will be. But whatever it is that you bury, make sure it's up to the task and can support the loads that you're going to be placing on it. Of necessity, a dead man is an improvised anchor. So it's something you would use as an anchor of last resort. Okay, multi-tool anchors. Based on the testing that we've done, multi-tool anchors are not an efficient use of the hardware that's available to you. If you have, say, 2 ice axes or an ice axe and a picket, you're better off making 2 separate independent anchors and then equalizing them together. So a lot of textbooks will show you this type of configuration where they say, place your ice axe in the snowpack, clip off to the top of it, and then take a second ice axe and lay that across the top to prevent the green ice axe from rotating forward. So in the testing that we've done, the single ice axe, and this is done in summertime snowpack on the slopes of Mount Rainier. So we're dealing with super high density, very, very strong snow. And the snow anchor, or the single ice axe placed in this configuration held anywhere between 900 and 1,600 pounds. The 2 tools in this configuration, where the magenta tool is about 6 inches below the surface, it tested out not significantly different than the green tool all by its lonesome. So adding the magenta tool, you could argue lowered it, but the difference is within the noise. It didn't do anything to substantially strengthen the snow anchor. So you'd be better off planting this magenta axe, 5 feet over to the left, and then equalizing it as a separate anchor placement. We also did a test where we took a horizontal picket, buried it about 18 inches down, and used that in conjunction with a vertical placed ice axe, and then we tied off to the center of the ice axe and the center of the horizontal picket. The 2 tools combined had a strength of just shy of 2,000 pounds, whereas the individual strength of the single ice axe, averaged it out to maybe 1,000 pounds. Average of this maybe 1,400, 1,500 pounds. You're better off with 2 independent placements than combining it. And the reason for that is actually fairly simple. All of these anchors failed in shear, so we took a wedge of snow and it popped out of the snowpack. By adding a second tool, we may have changed the shape and surface area of that wedge of snow slightly, but not significantly. If we were to take these 2 pieces of hardware and bury them such that each one created its own separate wedge of snow that popped out of the snowpack, we're effectively doubling the strength of our anchor system. If you're going to place 2 snow anchors in parallel, the ideal edge-to-edge separation is going to be 4 times the depth of the deepest part of the thing that you're burying. So for horizontal picket, it would be 4 times the depth of the carabiner. And that would be so that the size and the extent of the shear cones don't overlap out here. Now, if you place your horizontal pickets too close together and you have some finite angle where you're bringing the 2 anchors together to a virtual anchor, what you can get is a lot of overlap in your shear cones out here. So you're effectively overloading this area here. This is going to see twice the load in this area as the snow out here. So this area will effectively be not supporting much of the load at all. So if you really, really like doing geometry and trigonometry, you could calculate what the optimal separation is for 2 horizontal placements. If you have a pair of horizontal pickets that you're placing with a 1 foot burial depth, you're going to want them to be 4 feet away from each other. Okay, that's edge to edge. So your carabiner distance would be about 6 feet if you're dealing with 2-foot pickets. If you have a 30-degree half angle, so 60-degree included angle here between the two tethers coming out of the snowpack, then you're going to want your edge-to-edge separation to be closer to 6 feet. Okay, carabiner separation closer to 8 feet. Now, with a Sierra picket, because the tip of the picket is going to be deeper, your separation is going to need to be deeper. So a 2-foot Sierra picket with a 1-foot barrel depth, you're going to want it to be 4 times that tip separation, so 8 feet in the scenario where you're pulling straight away. If you have that 30-degree half angle, now you're looking at 11 feet of separation. That's an awful lot of real estate for building snow anchors. Okay, if you only got 2 snow anchors or 2 placements in the snowpack, that's probably not enough that you want to trust somebody's life to it. Ideally, you're going to want at least 3 snow placements for each piece of hardware that you're burying into the snowpack. If you decide instead to place your anchors front to back, so put them in series rather than parallel, this requires less real estate. So again, we're looking at a 2-foot picket with a 1-foot carabiner depth. And so here it's going to be, again, twice the tip depth for separation. So for your horizontal picket, if your carabiner is 1 foot deep, you're going to want about 2 feet of separation between your placements. For a vertical placement, your tip depth is going to be 2 feet, assuming that you have the top of the picket at the surface of the snow. So twice 2 feet is 4 feet. So here we're now looking at 4 feet of separation. So this is what the shear cones look like in profile. So if you have twice the tip depth of separation, the shear cone of the rear anchor will not be affecting the shear cone of the forward anchor. Okay, and that's true for both the horizontal and the vertical placements. If, however, you place them too close together and you don't get adequate separation, now you will get overlap of those shear cones. And this is going to essentially take this volume of snow out of the equation. So the snow that's back in here will not be supporting your load because it's going to be loaded to twice the load as the rest of that shear cone. So this is something that you do not want to do. Okay, placing your hardware in series will require smaller footprint of snowpack, but you want to make sure you have adequate separation. So you want at least twice the tip depth of separation between the front anchor and the rear anchor. When you're equalizing your anchors, okay, do you want something that is self-equalizing or something that approximates a self-equalizing anchor? Or do you just want to equalize it, eyeball it, and tie it off in the manner that you would typically use a cordelet? The answer is you want to tie it off and not use a self-equalizing anchor. And the reason for that is that the anchor is the individual placement, so the hardware that you put in the snowpack is generally going to move at least a few inches when loaded up. And if you do a thought experiment and one of these starts to move at, say, 50 pounds and the other moves at 100 pounds, if you have a self-equalizing anchor, well, your master point is to start moving when you apply 100 pounds to it. Whereas if you tie it off and put a hard connection there, you'll be able to support 150 pounds before anything starts to move. So for that reason, we recommend a hard tie off. Okay, so all of the testing that we had done up until a few years ago was at low strain rates. So slow pull testing, either with a bunch of people on a mechanical advantage system or somebody cranking on a come along, or if you're dealing with a very, very strong snowpack, a bunch of people cranking on a come along that's connected to a mechanical advantage system. But eventually somebody asked the question, well, what happens if you do drop testing on it? What happens if you have that dynamic event during a rescue? Well, we did some testing. We found a snowpack down here in Southern California. So this is not quite Sierra cement, but it was a high density snowpack. We found a 30-degree slope and loaded up a Cascade litter, something with a nice smooth bottom that'll slide nicely, with pretty much 1 kilonewton of test mass in it. So that includes the weight of the rescue Randy, the litter, the backboard, and a little bit of extra ballast that we put in there. We pre-tensioned the knots to a little over 2,000 pounds, and we did that by doing some slow pull testing on some anchors to establish a baseline for the strength of the snowpack. And then we put 26 feet of rope into the system. And the way we do the testing is we would have the head end of the litter right up at the same level as the anchor. So the litter would slide 27 feet 26 feet along the surface of the snow, and 26 feet of rope would be used to catch that. If the system were arranged dead vertically, this would be a fall factor 1 scenario, but because we're dealing with a 30-degree slope, it's actually a fall factor of about 0.5, which is still a pretty severe fall. And here I have some videos of various tests. So we tested horizontal pickets, Sierra pickets, and flukes. So we'll run through these videos real quick. So here's a horizontal picket. 2, 3. And that one caught the load. And this is a horizontal picket. And that one did not catch the load. And our safety rope also failed. So our backup system suffered a failure on that one. That one, the carabiner broke. Okay, this is a Sierra picket. And that one successfully caught the load. And here we have a Sierra picket. And this is the top of the picket right here. Now you see it, now you don't. Here's a fluke. Okay, that one, the fluke was able to catch the load. And here, okay, the fluke did not catch the load, and the load went onto the backup anchor that was tied to a nearby tree. This is a bollard. Now this bollard started off fairly large. Now we did a drop test on it, and the rope cut through the back of the bollard. And so then we carved away that snow and did the testing again and again. And the bollard was surprisingly robust in the face of the drop testing. So then we decided, okay, let's remove the padding from the uphill side of the webbing. So here we're doing it the way the textbook tells you not to do it. Okay, so the nylon is directly against the snow. There is no padding there whatsoever. And this bollard right now is about 5 feet long by about 2.5 feet, 3 feet wide. 1, 2, 3. And the bollard caught the fall. Now we're dealing with a bollard that's down to maybe 2.5 feet long by 1.5 feet wide. Yep. 1, 2, 3. And there we finally got the bollard to fail by slicing through the mushroom stem. But it took quite a bit of doing to get that bollard to fail. Now, the caveat here is that this was high density, high strength snow. If you're dealing with champagne powder, the rope is obviously going to cut through things much, much more readily. A couple of eye openers. 3 of the 22 drop tests that we did that day resulted in hardware failure rather than failure of the snowpack. We broke a cable, we tore the eye out of a picket, and we broke a carabiner. And you notice that some of these strengths are shockingly low, like less than 1,000 pounds for 2 of those failures. In the remainder of the failures where we failed the snowpack, the strengths were typically 1/3 to 1/2 of the slow pull strengths. Now, when we first started doing the testing on this particular day, we did 4 slow pull tests with Sierra pickets. And in all the tests, the anchor tested to about 2,000 pounds, plus or minus about 100 pounds. So it was very consistent and very strong. In most of the testing that we did, particularly those where the anchor failed, the failure load was less than 1,000 pounds. And in all of the failures, the failure mode was in compression, where we simply tore the hardware through the snowpack. We did not eject a wedge of snow. One of the other points I'd like to make is that all of these anchors were tested in the same snowpack, having the same aspect on the same day with the same slope angle, using the same load applied to the system, that same rescue Randy sliding down the hill. And 60% of them caught the load and 40% of them did not catch the load. So, and all of these were built with the intent of catching the load. So that just underscores the variability of the snowpack and its ability to catch a load, particularly under dynamic conditions. Okay, people frequently ask me, well, what is the best type of anchor to use if you're building a snow anchor? And my response to that is, what do you mean by the word best? Most often when confronted with that, they say, well, what's the strongest? And if your strength is the only thing that matters, then we can answer that question. But there are other performance criteria that need to be considered. Speed could definitely be a consideration if you're dealing with a live subject. Easiest to remember, not everybody goes out and breaks snow anchors every summer or every winter like I do. So it's important that whoever's going to be placing these anchors remember how to do it properly. Is it important that this failure mode be graceful so that you can see it coming? Or do you not care about that? And is an abrupt failure acceptable? Some of these anchors will be more susceptible to snowpack layering than others. And if you're dealing with a snowpack that has lots of different layers in it, that may be the driving force. If you're not a big person like I am, how much does all this hardware weigh? And is that going to be a consideration? Coolest looking should probably not factor into the equation, but sometimes it may. Okay, so here are the trade-offs, and I apologize for this being somewhat of an eye chart, but if you're looking at strengths, a bollard is probably going to be the strongest anchor that you can place. Next down in strength would be a Sierra picket, followed by a horizontal picket, followed by a fluke, which would be much, much stronger than a traditional picket or a vertically placed ice axe, which would be the weakest possible configurations. In terms of how quickly you could set up one of these things, the traditional picket or the ice axe clipped at the top is by far going to be the fastest anchor that you can set. Sierra picket would be the next fastest since you only need to dig one trench. The fluke, you need to dig a little bit more to place one of those. Horizontal picket requires a little bit more digging still. Bollards and dead men require a lot more digging, so those are going to be the slowest. In terms of gracefulness of failure, if you have dense snow, then a bollard is going to be the most graceful failure mode because you can see your rope cutting into it. Sierra picket, you could actually see the top of the picket if it's flush with the top of the snowpack, and you can see it moving, so that gives you some indication that you're overloading the anchor. You could also see cracks starting to emanate from it before it fails catastrophically. Traditional picket and a vertical placed ice axe give you pretty much no warning. Neither do the fluke or the horizontal placed picket. If you're dealing with light, low density snow, then again, the bollard is going to be the more graceful failure. Fluke and horizontal picket, followed by the trad picket, and the ice axe will be the most sudden failure. If you're dealing with light snow that fails the snowball test, an ice axe probably will not support body weight, nor will a traditional picket, so beware of that. If you want insensitivity to snowpack layering, something that's going to be robust in the face of multiple layers, Sierra picket is probably going to be your best tool because it samples at least 2 feet, if not 3 feet of the snowpack, depending on how long the hardware is that you're burying. A dead man, again, depending on what it is that you're burying, perhaps a snowboard, will sample a greater thickness of the snowpack. Traditional picket could be your friend if you have icy layers, so you could take advantage of that layering. Flukes and bollards tend to be at the low end of the totem pole here, and then the horizontal picket is going to be the most sensitive to a weak layer in the snowpack. Finally, in terms of lightest weight, traditional picket will be the lightest because it essentially requires nothing that you're not already carrying. Bollard and a dead man require that you have a snow shovel with you. And presumably, if you're out in winter conditions, somebody in your group will have one of those. Flukes, that's a special piece of equipment that you would have to carry with you if you're intending to build a snow anchor. The fluke, the only thing you could pretty much do with it is build a snow anchor out of it. Flukes typically weigh substantially less than pickets for a given frontal area. So a fluke is going to be about 40% lighter weight than a 2-foot picket. If you're going with 3-foot pickets, then the fluke will be substantially lighter weight than that. So depending on what you mean by best, that's going to tell you what type of anchor you want to build. If you're doing a recovery up a 45-degree snow slope, okay, the loads are going to be low and you have the luxury of time. So yeah, you could let strength be the main driver on that system. The flip side, though, is if you have a critically injured patient in a crevasse and he's part of your climbing party, so you're right there, now speed is definitely going to start to play a role in your decision-making process. So let's look at a crevasse rescue scenario. And on the left side, we're looking at anchor strength. And on the right side of the spectrum, we're looking at speed. So if we build a super high strength anchor, we're building multiple 30-minute bollards. The way this could play out is that it's going to be a very slow rescue and your patient could succumb to their injuries. Now, if we trade off some strength for speed and move a little bit further down the chart, now we have a slow rescue and the patient's condition could deteriorate. So let's trade off a little bit more strength for speed. So now we have a quick rescue, we're able to provide timely treatment, and we get optimal patient care. But if we push the pendulum too far in that direction and compromise too much of our strength for speed, now we can have a situation that results in anchor failure and a second patient in the crevasse. So we definitely want to avoid this. So what this tells us is that we have a Goldilocks zone here in terms of the trade-offs of strength versus speed. And if you look at some of these other considerations, gracefulness of failure, snowpack layering, lightweight, et cetera, that's simply going to complicate matters. So speed and strength are the two easiest ones to look at, but there are other factors that you need to consider. So in terms of the best practices, know your snowpack, because ultimately that's what's going to be supporting the load. Do the snowball test and consider compacting the snow that you're going to be building the anchor of if you pass the snowball test. When you're deciding what type of anchor to build, you should consider all the factors, not just strengths. And you should consider all types of anchors, not just one. If you only have one bullet in your gun, don't go to the gunfight, okay? Have multiple bullets in your gun so that you can assess the situation, use the anchor system that's optimal for the conditions that you're working with. By all means, you want to minimize the load on the system and avoid dynamic loads like the plague. And assume conservative anchor strengths. We talked earlier about intuition and what your gut tells you that the anchor can hold. Well, your gut will provide useful information, but be very, very conservative. And because you're going to be trusting somebody's life to your anchoring system, for each rope you have in play, use multiple anchors. My personal recommendation is at least 3 snow placements for each system line that you have. So if you're using, say, a main and a belay line, you're going to want 3 snow placements for the main line and 3 snow placements for the belay. If you're using parallel systems, 3 anchor burials for one rope and 3 more for the other. Some of the worst practices that I've seen, assuming one size fits all. Okay, this is the guy who decides that flukes are the one size answer to all of my rescue needs, and he doesn't consider pickets. Or the person who considers only the Sierra picket and ignores horizontal placements or the use of flukes. Or the guy who only wants to dig bollards. Okay, one size does not fit all, so do not fall into that mental trap. Never ever use a Sierra picket if the snowpack fails the snowball test. Don't assume that strength is the only factor to consider, and the crevasse rescue scenario is a clear example of that, where if you have a live patient that's down in the crevasse. Allowing a dynamic event to occur. Just because the slow pull strength says, yeah, this thing could hold 1,000 or 1,500 pounds, that doesn't mean it's going to hold that much under a dynamic event. A lot of people, their sheriff's department or authority having jurisdiction wants them to have a 10-to-1 static system safety factor. If you have a big enough area to build your snow anchors, that's theoretically possible, but from a practical standpoint, it is absolutely a non-starter. If you want to build a 6,000-pound snow anchor for your main line and another 6,000-pound snow anchor for your belay line, you're going to have literally a forest of snow anchors out there. It's just not practical. Burying a non-locking carabiner at the anchor. Invariably what happens when you're backfilling the trench, you're going to open up the gate on that beaner. And as I'm sure most of you know, when you go from the gate close strength to the gate open strength of a carabiner, you're throwing away anywhere from 2/3 to 3/4 of the strength of the carabiner. And we have done slow pull testing on snow anchors with unlocked or opened carabiner gates where we deliberately pack it with snow. And sure enough, if we're dealing with high strength snow, we break the beaner. And then finally, there's absolutely no reason to build a snow anchor if you have a tree that's a piece of the earth 20, 30 feet behind you. Trees don't come with hang tags either, indicating what their 3 sigma mean breaking strength is. But as a rule of thumb, the vegetable anchor will be stronger than the snow anchor. And with that, I would be happy to open the floor to questions.
All right, Art, we got a number of questions here. I'll start here at the top. First question is, how many samples were there for each of the anchors? This was early in the presentation.
It varies for the different types of anchors. For dead men, I think the data set, we only have about 4 or 5 of those in there. But for some of the more common types of placements, the horizontal picket placement, the Sierra picket, and flukes, we probably have, let me say, a few dozen data points for each of those.
Okay. Next question. Loose isothermal corn to disturb or not to disturb?
Snowball or not to snowball. Okay, if you can make a snowball and it holds together, then compacting the snow will strengthen it. Now, corn snow is kind of a weird beast. Sometimes it will pass the snowball test and sometimes it won't. So it's going to depend on what the moisture content is of the snow that's right there at your feet that particular day.
Okay. Next question. In the horizontal picket slide, the picture appears to show the picket is girth hitched with a runner. I think you recommended using a carabiner to attach to the picket. Can you clarify the carabiner versus the girth hitch?
Yes, let me go back to that slide. Okay, this was an image I took from chickswithpicks.net snow anchors. So
we can't see it.
Okay, yeah, there's a reference down here when you actually, let me go back to this mode here, make it a little bit easier to see. Maybe not. Okay. Anyway, this is an image I pulled off the internet.
We can't see it. I think you have to go back into presentation mode.
Okay.
I think you may need to reshare.
Yeah. All right. Let me go back to presentation mode, and then I will reshare. Okay. Can we see that now?
Yep.
Okay. This was an image I took from the chickswithpicks.net website where they girth hitched the picket. I personally do not recommend that because it has a tendency to crush the picket and collapse its cross section. The Yates pickets that are in this configuration, you can get a carabiner through the 2 holes in the picket. There'll be one on this side, one on the back side that you can't see. That would be the recommended approach to securing to the picket. The other option would be to put your webbing through the holes in the picket so that you avoid this compression that you're placing on the picket. Also for V-shaped pickets with V-shaped cross sections such as this one, it's better to orient the picket in the opposite direction so that the point of the V is pointing in the direction of the load. By doing that, you distribute the force more homogeneously into the snowpack. Now, some of the pickets that are available out there commercially, they have a swaged cable onto it, and the direction that they swage the cable onto it will kind of define the direction that you're going to be doing the pulling, whether you like it or not. I think that answered the question. The recommendation is to carabiner yourself into the picket rather than to girth hitch.
Excellent. Did you test strength did you test the strength of Dyneema runner girth hitched to the center hole in lieu of using a carabiner?
I did not.
Okay. Next question is fluke. If the rake angle is adjustable, do you want to pull the fluke perpendicular to the pole or perpendicular to the snow surface? You said surface, but it seems to me that perpendicular would be the strongest.
This configuration is the strongest. So perpendicular to the surface of the snow. And ideally, your runner would be long enough that the direction of pull is as parallel to the surface as practical.
Okay. Next question is, with the vertical flute, is there not a component of force upward a part of the vector trying to pull the fluke up to the surface?
Yes, with any snow anchor that you bury, of necessity, this angle here is going to be non-zero, right? Unless you have an infinitely long tether, there will be some upward component on whatever it is that you're bearing, whether it be a fluke, a picket, horizontal picket, vertical picket, dead man, bollard, whatever. Correction, not a bollard. But yeah, if your hardware is below the snow surface, there will be some upward component on this piece of snow in front of it.
Okay. And then I've got a Mr. Smith who's going to challenge your thoughts on stuff sacks.
Okay.
In very dense and cohesive snow, I've had stuff sacks be strong on the order of 40 pounds per square inch. Key is to pack the snow really tightly in the stuff sack. We made the stuff sacks and have flat surface towards the load.
Okay.
What do you say to that?
Well, as an engineer, I don't argue with empirical data. Okay. If he tested it and got whatever the strength is that he measured, then clearly that particular anchor on that particular snowpack was able to hold that load. Where I'd be cautious with the snow, with a stuff sack full of snow, would be if you girth hitch it, that girth hitch will tend to squeeze the snow out of the middle of your stuff sack and turn it into something that's shaped like an hourglass, in which case you ultimately do become reliant on the strength of the nylon comprising the stuff sack. Now, let me point out that I have never tested a girth hitch stuff sack and gotten it to that point. So that is a theoretical consideration and not one that I've actually witnessed. And like I said earlier, I've only tested maybe a half dozen or so dead men and very few that were, in fact, I think only one that involved a stuff sack full of snow. So I don't have a ton of data. So if whoever did that test, I will look you up in the chat so that we could exchange some notes here. I'd be very interested in adding your data to the database.
Okay. Next question. In the HW in series, are you back tying to the pickets, creating a single anchor, or treating each picket as a separate anchor?
Okay, let me. Okay. When you view it from the side, it becomes a little bit more apparent that you want them to have separate tethers that go to the master point independently. In some testing that we did with Sierra pickets in series, we had the center point of this picket connected to the center point of this picket that was then pulled at some upward angle to the master point that we were loading. And as one of the previous people pointed out, what about that vertical component? And yes, there is a vertical component that was acting on this lead picket that prompted it to pop up and out of the snowpack when the load out here was high. And because this lead picket was now unbalanced, part of it was extruded from the snowpack and part of it was still supported, the front picket was now out of balance and it started to rotate forward. And then once it rotated forward, its ability to hold the load was dramatically decreased. And so the bulk of the load was then being supported by the rear picket. Okay, so two separate tethers to your master point would be the preferred way to load up your hardware in series.
Excellent. Next question. In your paper titled Snow Anchors for Belaying and Rescue, you mentioned that skis can achieve a similar strength to pickets when buried sufficiently deep in the vertical mid-clip configuration. You mentioned that dead mans should be used cautiously due to their improvised nature. Can an MRA team of skiers rely on skis in lieu of pickets, given that they perform similarly to pickets in snowball tested snow and perform better than other options in dead man or snow packs that fail the snowball test?
I have limited data on skis. We've done a few tests, and for the most part, we chickened out when we felt that we were in danger of breaking somebody's ski. I think the most we loaded up a single ski to is probably about, actually, let me not guess. Let me pull up that data real quick. Okay, we loaded up a single ski to 2,500 pounds on one test, and we loaded up another ski to a little over 4,000 pounds on a separate test. So based on those two data points, which are the only data points I have for skis, I would say that a ski is probably a safe placement, but like any snow anchor, you don't want to trust your life to a single placement. So if I were going to use only skis to build a, say, main and belay type system, I would bury 3 skis for my main line and another 3 skis for my belay line. But again, I have limited data. So if somebody out there has some additional data on the strength of buried skis and different types of snowpacks, please share that with the group.
Excellent. The next series of questions just reveals how popular this presentation is, because everybody wants to know how soon it's going to come out on YouTube. So we're going to work on getting that out in the next couple weeks at the latest, hopefully a little sooner, and we'll work on that. Next question is, during drop testing, did you vary the location of the tests in parentheses to get out of the cone of compression failure?
Yeah, we varied the location of the burials by several feet, but not by 10 to 20 feet, because all the failure was in compression. The snow that was ejected from the snowpack, well, it was no longer there. So we were able to backfill that, but for the most part, we were inching our way down the hill as we went to successive anchors. So we'd index our way horizontally across the top of the slope, and then drop down, 4, 5, 6 feet, and then dig another snow anchor, and then work our way horizontally as we did additional tests, and then index forward another, 5, 6 feet, and then continue doing tests in that manner. So we tried not to use previously tested snow in the snow anchors for subsequent tests.
Excellent. Next question, on the drop test failure of the wire rope, what failed? Was it the wire rope or the swage?
The wire rope itself failed.
Okay.
And we've also failed wire ropes in slope pull testing.
Okay. Next question is kind of a response question. It usually takes us hours for us to be notified, pack, and reach a scene. How likely is it that the extra half hour will make a significant difference on patient outcome?
That depends on the condition of your patient. If they're on the ragged edge of survival, then time might make a difference. If they're stable and they're going to stay stable one way or the other, then that extra half an hour, it will impact their comfort and suffering, but probably not their long-term outcome. But that's really a medical question.
Yep. Next question, is there an advantage? Oh, I just lost it as somebody put in there. Is there an advantage to offset 2 side-by-side anchors?
I'm assuming you mean front to back offset.
Yeah.
I hadn't considered that. Let's see. So if we're looking at, say, 2 horizontal placements, if we were to take this one and move it back, that would enable you to move it laterally, so it's more inline. So that would enable you to use a smaller snowpack area to build your anchors. So if parallel is your preferred approach for whatever reason, then offsetting it front to back will enable you to get by with a smaller footprint.
Okay.
Minimum footprint, though, would be placing them in series.
Okay. This is outside the presentation, but they're interested in your thoughts on ice screws when applicable.
Mark Beverly and Steve Attaway did an excellent IDERS presentation years ago on ice screws. And I believe that's available at idersonline.org. So I will defer to that as the seminal work in that area. but they did a lot of testing, looked at different angles of placement of the ice screw. And I'm going from memory here, but I believe what they determined was that the ice screw is angled in the direction of pull slightly. Okay, not tipped back away from it, but in the direction of pull. That gives you a stronger anchor.
Excellent. Next question. Is the 30-degree angle for the stress cone measured from the plane perpendicular to the picket, i.e. interior angle of 60 degrees between the picket and the runner, or is it 30 degrees from the surface plane of the snow?
We don't have enough data to really say one way or the other. In much of the testing, let me go back here, whether it's by accident or design, in the horizontal placement, for the most part, the angle that the tether is coming out is also at about 30 degrees plus or minus. So the angle of shear failure here, we don't have enough data to differentiate whether it was caused by the angle of the tether or the mechanical properties of the snowpack or the rake angle of the fluke in the case of the fluke. One of the things that we determined early on is that for the fluke, by going perpendicular to the surface of the snow, we got the greatest amount of strength. So because of that, we didn't do a whole lot more testing with this. Now, we still have quite a few data sets or data points in the database where the fluke did bury itself down deeper into the snowpack. But invariably, when we were testing with an angled placement, if we didn't get shear failure, if we got compressive failure, invariably the fluke would dig down until it found either a weak layer, in which case it collapsed and just skated across horizontally through the weak layer, or it found a hard layer and when zipping along the surface of the hard layer in a manner that looks like this, where it collapsed the front wire and just started skating along that hard surface.
I see. Good explanation. Derek just wants to point out, if you want to go to the chat box, there's the largest repository for snow and ice anchor data is at a website that's there in a chat box. And then Charlie's responding that he's going to work to get this presentation out by Monday on YouTube. And that's the end of the questions. Art, just an excellent presentation, and we had a record-breaking audience for Third Thursday tonight.
Well, thank you everyone for foregoing the Olympics in favor of playing in the snow or the virtual snow.
Excellent. Well, this wraps up our Third Thursday. Please join us in March, and remember that it's going to be the fourth Thursday, just because we didn't want to compete with St. Patty's Day. I know that's important to many of you folks out there. And we have Echelon coming out to do a fantastic leadership presentation. And lots of accolades, Art, for this presentation.
Okay, thank you very much, everyone.
Have a good night. See you next month.